Good morning. Today we talk about conjugate operations and classes. The symmetry operations of a group can be broadly divided into a few classes. A class of operations are those which are conjugated to or similarity transform of one another. All operations which are conjugate to one another constitute a class. To find the conjugate of an operation, you have to carry out a procedure known as similarity transformation. Suppose you want to find out the conjugate of an operation, say B. You right multiply it with an operation X and left multiply it by an operation X inverse. Now this procedure is known as similarity transformation. After doing this, suppose you get the result as A, another operation. We say that A is the similarity transform of B by X. A is the conjugate of B by X. Remember that the operations A, B, X and X inverse all belong to the same group. We shall illustrate classifying into classes with the operations of C3b group to which ammonia belongs. C3b operations are identity C3, C3 squared, sigma v dash, sigma v2 dash. For our reference, I have written here the group multiplication table for C3b. First you find the similarity transform of identity. You multiply it with any operation of the group X and its inverse to the left side. We know identity combines with any operation, leaving it unchanged. So this is essentially X inverse. Inverse is such an operation that it combines with the original operation to give identity. So whatever be the operation X, identity is conjugate only to identity and nothing else. Therefore, identity always forms a class by itself. Now, think of C3. You can first try with identity. Inverse of identity is identity. Identity into C3 is C3. C3 followed by identity is C3. Then you try with C3. C3 right multiplied by C3 and left multiplied by inverse of C3, which is C3 squared. Altogether it is C3 to the power 4, which is C3. Then you try C3 squared, C3 right multiplied by C3 squared, left multiplied by its inverse, which is C3. Again you get C3 to the power 4, which is C3. So you are getting as the conjugate of C3, C3 itself so far. Now do with sigma v on the right side and its inverse sigma v on the left side. In order to get the product of sigma v and C3, you look to the multiplication table. Sigma v C3, it is sigma v2 dash, sigma v2 dash, sigma v2 dash into sigma v2 dash into sigma v is getting C3 squared. So C3 has a conjugate C3 squared. Then C3 sigma v dash, find sigma v dash C3. sigma v dash, C3 is sigma v, sigma v dash, sigma v dash, the product is C3 squared. Lastly, with sigma v2 dash, C3 sigma v2 dash on the right side, sigma v2 dash on the left side. Combine these two, sigma v2 dash C3, sigma v2 dash C3, it is giving sigma v dash, sigma v dash, sigma v2 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 dash, it is C3 squared. So apart from C3 itself, C3 is conjugate or similarity transform to C3 squared. Therefore, C3 and C3 squared together will form another class. Now find out the conjugates of sigma v dash and sigma v2 dash. First you take sigma v, identity, it will give sigma v itself. Every operation is conjugate to itself, and actually it is a trivial result. Our aim is to look for other operations to which a particular operation is conjugate to. Then sigma v C3, the inverse of C3 is C3 squared. C3 sigma v, C3 sigma v is sigma v dash, C3 squared. What is sigma v dash C3 squared? Sigma v dash C3 squared is sigma v2 dash. So sigma v is the conjugate of sigma v by C3 is sigma v2 dash. Then sigma v C3 squared and its inverse is C3. Find out the product. C3 squared is sigma v, C3 squared, sigma v is sigma v2 dash, sigma v2 dash C3, sigma v2 dash C3, it is sigma v dash. So sigma v dash is another conjugate of sigma v. Then sigma v and its inverse sigma v, it will be definitely sigma v. It is a trivial result. Then sigma v dash, sigma v dash, sigma v dash, sigma v dash, sigma v is C3, C3 followed by sigma v dash, C3 followed by sigma v dash is sigma v2 dash. Lastly, you take sigma v, multiply it with sigma v2 dash and its inverse, which is sigma v2 dash itself. Associate these two, get the product from the multiplication table. Sigma v2 dash sigma v, sigma v2 dash sigma v, it is C3 squared, C3 squared sigma v2 dash. What is C3 squared sigma v2 dash? You have to come here. It is sigma v dash. So we find that the particular operation sigma v is conjugate to sigma v itself. Other than that, it is also conjugate to sigma v dash and sigma v2 dash. That is sigma v dash and sigma v2 dash are conjugate to one another. These three will form another class. There are some theorems regarding conjugate operations. Every operation is conjugate to itself and it is a trivial result. In the case of abelian group, every operation is conjugate only to itself. and that is an important result. Abelian group. Every operation is conjugate only to itself. Suppose A is an operation of abelian group and X is some other operation. Its inverse is X raised to minus 1. This is the similarity transformation procedure. Being abelian, X followed by A can also be written as A followed by X. And if you associate these two, X and X inverse, whatever be X, it is identity, and identity into A is A. So in our attempt to find out a similarity transform of A with other operations, whatever be the other operations, you always end up with A itself. That is why we said in an abelian group, every operation is conjugate only to itself. Then, if two operations A and B are conjugate to each other, if A is conjugate to B, then B will be naturally conjugate to A by some other operation. They will be mutually conjugate. And if A is conjugate to B and also C, then B and C will be conjugate to each other. The only foolproof method to find the conjugate of an operation in a group is follow the similarity transformation procedure as we have demonstrated for C3b group. But it is very tedious. Therefore, we rely on some shortcuts or some tips or some rules to find out the classes of operations. Make a special note of these rules. We no more need this multiplication table, so I am rubbing this off. This was the model of ammonia with a reference to which I wrote this multiplication table before the video classes started. Some shortcut methods to know the classes of operations. I list here, make special note of that. Firstly, identity, center of symmetry or inversion, and sigma h. Each of these is always a class by itself. They are not conjugate to any other operation than themselves. Secondly, if Cn raised to k and Cn raised to n minus k, they will belong to the same class if there exists in the molecule n sigma v's or n C2's perpendicular to Cn. I repeat, Cn to the power k and Cn to the power n minus k will belong to the same class if the molecule has n sigma v's or n C2's perpendicular to sigma v's. If these conditions are not present, then Cn raised to k and Cn raised to n minus k will belong to separate classes. For example, in the Cn group, there are no sigma v's or C2's perpendicular to Cn. Therefore, the operation Cn, Cn squared, Cn cube, etc. up to Cnn, which is identity, each of these will be a class by itself. This particular rule applies to a molecule having S n axis, that is Sn and Sn raised to k and Sn raised to n minus k. They will belong to the same class, provided there are n sigma v's or n C2 perpendicular to Cn. For example, for benzene, which is D6H group, the C6 and S6 and S65, S61 and S6, 6 minus 1. These two belong to the same class because benzene has N sigma V's as well as NC2 perpendicular to the C6 axis. Then equivalent symmetry elements or operations always belong to the same class. What do you mean by equivalent symmetry elements? These are symmetry elements bar operations which can be interchanged by the application of some other operation existing in the molecule. For example, in the ammonia group, sigma V dash and sigma V2 dash, these three can be mutually exchanged by a C3 operation or C3 squared operation. So all the three belong to the same class because they are equivalent. But in a group like D4H, to which platinum tetrachloride complex belongs, square planar complex, it has four sigma V's. Let this be sigma V, and let this be sigma V dash, and let this be sigma V2 dash, and let this be sigma V3 dash. DNH group has CH group, NC2, sigma H, and N sigma V's, and these are the sigma V's. Sigma V dash, sigma V2 dash, and sigma V3 dash. Here we have two sets of equivalent operations. Sigma V and sigma V2 dash, they can be mutually exchanged by C4 operation. So also sigma V dash and sigma V3 dash, they can be exchanged by 90-degree rotation. But there is no operation existing in the molecule to exchange sigma V with sigma V dash. Therefore, we have got two sets of equivalent operations of the sigma V type, and hence two classes, which are the classes sigma V and sigma V2 dash. This will be one class, and sigma V dash and sigma V2 dash will be another class. This is generally the case if the N value of the DNH group is even. So also for CNV group, there are N vertical planes. If N is an even number, there will be two sets of classes among the vertical planes of symmetry. The operations of a class should be of the same type, either all rotations or all reflections. Rotations and reflections do not mix in the formation of a class. Then a few more tips we can add towards the end of this class. The DNH and DND groups, the total number of operations is given by the formula 4n. They will contain as many as 4n operations. For example, D3H, to which boron trihalides belong, they will have 4 into 3, 12 operations. Benzene belonging to D6H, where the N value is 6, will have 4 into 6, 24 operations. If in the DND group all the NC2 axis perpendicular to Cn will belong to the same class. But in the DNH group, if N is even, the C2 axis perpendicular to Cn will belong to two different classes. Then, regarding products of operations, the product of any two proper rotations will also be a proper rotation. These are some tips which will be helpful to you in the pursuit of group theory. We know C2x into C2y is easily proved to be C2z. Product of two proper rotations is another proper rotation. This is not true with respect to reflection. If there is a sigma in a plane A and there is a sigma in the plane B, the product of these two, if the two planes make an angle of phi AB, the product of these two will be a rotation by an angle of 2 phi AB. For example, in ammonia, sigma V and sigma V dash are two planes making an angle of 60 degree, and the product of these will be an axis which is coaxial with the line of intersection of these two planes, which has the symmetry by rotation of 2 into 60 or 120 degree. It is a C3 axis. C3 axis and the line of intersection of the two planes are the same. Regarding commutative properties, the operation I commutes with all other operations, reflections and inversions. Any two rotations about the same axis will always commute each other. You can remember these tips for future easy dealing with further ideas on group theory. This is what I was planning to tell you in this particular video. Thank you very much.